Hello, good morning, everyone. Today I'm going to talk about Lattice Boltzmann Method, and we're going to look at a special case called the driven cavity flow to show why Lattice Boltzmann Method is one of the good way to draw computational fluid dynamics flows. Right now, what we're looking at is a Formula One car. I like Formula One car. One, I'm an engineer, so I like building stuff like powerful raw power and like machines. And when people talk about Formula One car, they always think about it's about power, like Jeremy Carson would say, power like that, braking and tires and things like that. But what the most people don't know about Formula One racing is that it's not only about power; it's also about fluid flow. So, or I would more like to say it's like drag. So, drag. What am I talking? What is drag? Like what kind of drag you talking about? So, I'm talking about the drag. Let's think about this. So, imagine a car that's going really fast, and you have seen in the videos if the plane is going really fast, it's trying to like fly because of the Bernoulli's theorem. Because the uh, I totally forgot what I'm talking about. But anyhow, going back to the point, if I go really fast, the car is gonna try to fly. So to counteract that, they the engineers did a pretty neat way of putting some wings at the front, so it will keep it to the ground. As the generation of cars started doing at each and every iterations, they try to improve the wings to make keep the car fit to the floor, keep to the floor, and that's what we are seeing in here. So they take this picture. What it shows is like a Formula One car has a front wing by the nose at the front section, and as it goes through wind tunnel, we can see the air is going like over its body and with a beautiful colorful lines. And that's what I wanted to talk about. These colorful lines are called streak lines, and I'm gonna show you guys how to a different way of getting this line. So let's talk about this line. So these lines are called streak line, as I said, and this is we can get it from using computational fluid dynamics, or CFD. And let's go to the next page. And what is computational fluid dynamics? Computational fluid dynamics, or CFD, is a set of methodologies which provides a numerical solution and a fluid flow, that should be flow pattern, over a surface area. The traditional approach is a kinetic theory. Kinetic theory. So what is kinetic theory? So kinetic theory assume that a molecule is a very small relative to the discrete distance between them, and a constant random motion while frequently colliding with each another with the walls. So think about it like this. So I have like a huge box. Inside of the huge box, I fill up with gas. As you know, the molecules of the gas are really, they don't have any interaction with one another. Like, we do have interaction, but they're not closely packed together. When you think about like a metal, yeah, all the molecules are dense, and like that's why they're so strong. So when it comes to the gas, they keep like they all are vibrating in a random motion, like they're hitting the balls coming back, like getting boom 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 like that. So take that big Formula One car and put it in this box. So think about a really big box, and there's a Formula One car, and from one side you're gonna put a fan on, and it's gonna blow the air. So when the air is started moving on the direction of the flow, as it goes through the body of the passes through the body of the Formula One car, is gonna. That's how it creates the lines that we saw in the previous lecture, the previous slide. So that's what's happening. So that's how they traditionally used to do computational fluid dynamics using kinetic energy theorem. So the most important part things that I talk about when I say is that it says constant random motion. So every time when we have something random, it's really hard to predict what's next. Or it is you can predict over through all a 10,000 iteration, but the calculation itself will become more complex because like it's a random motion because there's no order. So let's create an order in this random motion, so at least we have like a basis, something like, you know, like if I do this, I know this will happen. So that's what I was gonna go for. So let's begin to create a order in this random motion. So that's why the lattice Boltzmann method comes in. So it's a relatively new method approaching hydrodynamic solution. Hydrodynamics like air, gas or liquid. It is the simplest form of kinetic energy theorem, but it doesn't model the system on microscopic scale, but on the memoscopic scale. So it's like microscopic because I said in the previous slide all the particles are in the motion, but what we're doing here right now is like zoom out of the picture, but still we're gonna talk about the small particles moving, but in a bigger scale. So we don't have to worry about the each and individual like particles like motion of them. So like we will have something bigger to handle with, so it's much easier. So what is memoscopic scale? So it's a scale used to study the condensed matter physics. The scale can describe material size both from atoms to material can be measured by micrometers such as hairs width of the hair. So let's go to the next one. So this is the general derivation how we can get the lattice Boltzmann method, which is in the middle. So one, you can get it from a lattice gas automata. It's fundamentally purely physics. Physicists has worked on that for a long time. Then another one is the lattice Boltzmann method. It's purely mathematics. It's just like hardcore mathematics. But the top one is a Navier-Stokes equation, because in engineering school we learn Navier-Stokes equation so in depth, like fluid flow through a pipe, and even in the gas turbine, and throat of gas, how much is going to create the Mach number, and how much speed is going to come out of the when it leave out the compressor and everything like that. So Navier-Stokes equation is part of engineer's life. And what happened was, if I could give you a backstory, people tried to create a Navier-Stokes equation from lattice gas automata. So they were doing physics, Navier-Stokes equation, boom. In the middle, they found this wonderful equation called lattice Boltzmann equation that connects all of them, but at the same time easy to do it, because Navier-Stokes equation, I think I got it. I think I'm thinking about right. I think it's right, where it requires a integration of the bodies, or a lot of integration in there. But I'm going to show you the lattice Boltzmann method, which is so easy to do, and you can get the results in boom. Like, but it's still going to need a lot of computing powers. So let's go to the next one. Let's talk about the history of the lattice Boltzmann method. So it's a little derivative from lattice gas automata, which I said like is on the way of deriving the Navier-Stokes equation from the gas automata. They found this awesome equation, and it's like a cellular automation used to simulate fluid flow. Yeah, because we have simulating the flow of the each cell, each of the fluid flow. So next thing is, it is built a basic foundation of LPM. So it gave it like the lattice gas automata gave us a basic foundation of lattice Boltzmann method, which is at a given state, either S or S naught, a particle moving in each direction. So it's just like saying Newton's, what's the second law's theory? If a particle is moving at rest, it will be at rest, but if a particle is moving, it's keep moving. So but it's nothing rigid to that, but it's like one of the laws saying like at the given state, if the one is at rest, is it going to be at rest? If it's moving, it is going to be at moving. Next thing, so this is the last top point. That's the most important part of the whole page. or even the whole presentation. So we know from kinetic energy theorem that all the particles are in motion, and when you try to do a calculation, it become more complex because everything is like moving around everywhere. What we're doing right now is we're gonna create a world or mesh inside of the system where it's like a grid, like a structure where we can like put every particle at its given position all the time. And if I want to look for it, I just see there and boom, it's right there. And every particle is like equally spaced, like 5 centimeters from here, 5 centimeters from here, 5% at the top, like like equally perfectly arranged. So that's what happened in here. So in 1986, a hexagonal grid model was introduced by these three physicists, and it's called as FHV model. This FHV model is constructed a microscopic world using Boolean variables or Boolean tensors. If you want to be deep, variables represent the particle by space-time velocity. Well, first of all, do you want to represent a particle, you need to know x, y, z, and give it time. But that's fundamental. You should know that. Everyone should know that. Then velocity does another part. Giving a to last term velocity, we need that. So this is the model. So it's pretty much like a carbon. Like carbon has 6 neighboring atom bonds. It has 6 atoms at the outer valence, and it can create 6 bond outside. What goes to silicon as well, and we are still carbon based model. We are all a carbon based what's the animals? Yeah, I don't even know. Should have things says. So yeah, so this what I said is 0 is this in center. That's the center atom, and it's surrounded by 6 particles, and they're gonna move in by the direction that I showed. It's like connected, like one is like in horizontal axis, another one is 2 are like going 45 degrees between 2 x and y axis. So that's how it's gonna particles gonna interact. So if particle number 1 is going through particle number 0 or center of the atom, it's called colliding. So it's just like colliding. So, or we can say from after so even from 0 to 2 we call it streaming. So like this particle is going towards the particle number. It's from 0 to 2, so it's going from 0 to 2, so it's like streaming. So these are the two things about collision and streaming, which we can see in the next slide. So FHV model proceeds in 2 motion. One is collision, other one is streaming, which we said just can't explain it in the previous slide. So in this slide it says if you look at the picture on the right, it says like one is like going to the center of atom, so it's like going colliding with it, the atom. Then once it's colliding, then the second part is like streaming back, so it's like a momentum. So like 2 particles are hitting together and it's returning back the same path, but it's in opposite direction. The next part is something that's not that important, but I like to say that it's just like it's one of their basic fundamental, and they derived it like this is how they represented it. So the Boolean both motion has rules, and following is the the following is the Boolean 6th order polynomial rule to given terms frequency factor, and I think that's sigma. Should check my Greek letters. So we have n1, if you look at the first picture, so whatever is coming towards the center of the atom, so we put it like n1, n2, n3, n1, n3, n5, then n2, n4, n6 are off. So these are, think about like paths. Then the second part of the after is collided at streaming. So n2, part 2, 4, 6 are turned on, and part 1, 3, 5 are turned off. So it's not that important, but it's just like saying like that's how they started to describe everything. So it's like really complex matrix, and like you have really uh, big number set. So that in the early time. So what we're gonna see in the upcoming pages is like how they got simplified and how we got to the Lattice Boltzmann method equation. So in the 1954, it was a long time ago, before early at the out of nowhere, someone like created an equation called, like, by these three physicists, a single relaxation time. So that's what it says, like single, like you can understand, like single relaxation, like how long is it gonna take, how at what speed each particle is going to reach relaxation, which the next point says a single relaxation time controls the rate of the time each equilibrium, and is depends on kinematic viscosity. Well, it's a fluid flow, so we can have kinematic viscosity, obviously. More information, we're gonna see more about this later on. So first we saw, with all this complex motion from the kinetic energy theorem, this three FHP model that gave us like a structure. It's like, okay, like I have all this complex motion, but I'm going to give an order to that. But in that equation, the Boolean variables, they're so big. Like, every point there's like one matrix, second matrix, third matrix. It's like each particle, if it got 3D, then it's going to be 9 matrix on. It's complex at the maximum level, and you need to have like high computers to do all the complex matrix. Unless if you have Fortran, it's just like create a cell, boom, change it, next. It's easy to MATLAB is gonna take years to do that. So what people did is, like, we have this matrix. We have this structure, and let's use a single relaxation time principle. It is also equation, but it's more simplified. It's just like, you will see the upcoming slides, it's like such a simple equation, but it works very well. So they combined these two and they got the Lattice Boltzmann method. Now we're gonna see what's Lattice Boltzmann. And when it comes, also one of the good things about Lattice Boltzmann method is like the boundary conditions are really easy to implement. You don't have to go through a hassle of doing complex Lagrangian Eulerian transfer, because when it comes to we're not going to talk about in here Amos boundary. There's a complex transformation between Lagrangian boundary condition to Eulerian points in the mesh, which is fun, but which is the next level of lattice fluid flow, but we are not going to focus about that today. Why the Lattice Boltzmann is good, and you can see the picture, like high quality, like you can look at the high accuracies of the results. At the same time, you don't have the so complex equation in the fluid continuum mechanics from Navier-Stokes equation. As I said, really complex algebras. So that's why the Lattice Boltzmann method is really good. It's simple and results are high. So I have a list of stuff. I suppose methods advantages. One is like microscopic properties are not essential, because as I said, we're not going to look at the small tiny particles in the molecules. We're just going to zoom out, then look at this at a really big scale. Even though the molecular going back to the point, even though the changes in the molecular interaction affect the transportation properties, but it doesn't alter the basic form, because we're not looking at the smaller particle. It replaces the Boolean variables with single particle distribution function. The big algebra has been replaced by simple equation, makes our lives easy, and boundary conditions are easy to implement. We will see why it's so easy to implement, and ideal for parallel computing. Well, they used to do sequential computing a long time ago, but right now it's everything in parallel, so two results are at the same time coming out, saves the time, and most of the supercomputers are great for power computing and get the results we can get it in a shorter period of time. So a couple of applications. Method of most of the hydrodynamics, as in a board going through a water or blood flow or any flow, it's easy to use CFD, LBM method. And also the flow through porous media. So for porous media, what I mean is like flow through a sponge or water filtration. It's like easy to uh, get the results, because all I have to do is like put the boundaries or put some random points in the box, and like we can get the results. And magnetic hydrodynamics, we're gonna look at that. That's something too deep. We'll just stay in the methods of hydrodynamics. So we're gonna derive this equation. Well, not like technically derive this equation, but we're gonna do our best to understand what's happening in here. So fundamental principle: control volume space was selected. Each particle in that space was sent to one point in a mesh. So yeah, engineering, there's a control mass control space. Well, it's more like in a thermodynamic, but it's still like big area. So we're gonna choose a one space control volume, and since we assign the order to this random motion, we have this mesh, and we have two kind of mesh. One is FHV and the DTQ9. We're gonna pick the DTQ9, but either way, it has points in there, so we're gonna assign every point to one particle. And when the system is disturbed by an external force, all the particle in the mesh will experience two continuous steps from its initial state. We're gonna see in the next slide what are the two continuous steps. Upcoming steps. So this is pretty basic. Time. You have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 time steps. Discrete lattice points. So 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, because we have in a mesh. And a fixed number of direction in the lattice velocity. Yeah, this is something really important, but we're gonna see it soon. We're definitely gonna see it soon. So this is the DTQ9 matrix. What it's essentially saying is, then one at the middle is mark number 1 is the central particle that we are looking for, and it's gonna interact or disturb by the neighboring 8 particle. So 2, 3, 4, and 5 on the axis. 6, 7, 8, 9 is gonna interact with diagonally. It's simple, yeah. And we're gonna have another box right next to it, and it's like a big continuous matrix. So yeah, so a long time ago I said, no, not long ago, 2 or 3 slides ago said, one is a control volume, another one is like each particle is going to do 2 continuous steps. So these are the 2 continuous steps. One is a streaming. Each particle moves to the nearest node in the direction of the velocity. Then once it arrives, it's going to hit the particle and it's going to collide. Then it's going to be like 2 continuous steps, like streaming, collision is going to happen continuously. So continuous steps are well, we know it's a DTQ matrix, so it's going to have equal spacing and 8 neighboring atoms. We already mentioned that. Particle can move at any one of their neighbor along as the links in one unit step. So at one time, it can go in one direction. This is something I said very long ago, slides before, as in compared to Newtonian second law, is like either particles at the stop, rest, or particle is moving in one direction. So yeah, so I'm repeating in here: particle can move any neighboring atoms alone in the links in one unit step at a time. So 1 t is equal to 2, or t is equal to 3, or t is equal to t, it's going to move in one direction only. And the particles are connected diagonally and axially, yeah, because particle 2, 3, 4 are connected axially, and 6, 7, 8, 9 are connected diagonally. So in the continuous step, when it's moving, it's going to have velocity, obviously. When a particle, when something moves, it's going to have velocity. We don't care about acceleration in here, but we only care about velocity. So if it's moving axially, or if it's at rest, speed is at 0. If it's moving axially, we're going to give speed is equal to 1. So it's a magnitude of speed. And particle moving in the diagonal direction, we're going to give speed of root of 2. Well, because it's like a right triangle, so 1, 1, root of 2. So we're going to continue with the Lattice Boltzmann boundary condition. So I already mentioned this earlier. One of the good things about Lattice Boltzmann method that I use is the boundary condition are easy to implement. There are many boundary condition. I'm gonna only talk about these two that are important for me to explain the experiment that we're gonna do later on. So first one is bounce back boundaries, and the second one is corner boundary. So bounce back boundary is like pretty much like a wall, and the corner is like if you have a box, the two corners, or three corners, or four corners. And always remember at the wall there's zero velocity because due to friction. So finally, so we have a two-dimensional square boundary. Lattice Boltzmann method because that's what we're picking. So that's our matrix from a random motion to matrix. And there are three type of particle x's. One is its rest, one is moving, another one is moving diagonally, one is moving diagonally, another one is moving axially. And the occupied in the space, that's the particle represented by a single particle distribution function. So all these complex Boolean variable go away and we use the single particle distribution function. And also the single particle distribution function can be a particle density distribution function, but both are the same. We use the single particle distribution function. So for simplicity, let's put a particle point A is represented by x, y, and t. So we only take on 2D. We're not doing 3D. And after t second, it's going to move. So it's going to have from x plus delta x, comma y, comma delta y plus t. So t is equal to 1. Then after 2 seconds, it's going to be 2, like something like that. So delta t. During the motion, it's going to particle as in the velocity. So we are not worried about what's the magnitude of velocity, but we just putting it as v. So delta v is equal to delta x over delta t also. So ex, we mentioned that we represent the velocity in terms of like e. So that's the sign that we pick. So ex is equal to delta x over delta t, and ey is equal to delta y over delta t. So we can just a little bit of rearranging. And one of the good thing about this rearranging is like pretty conventional, the method that covered by most of the physicists and most of the journals have this method. So that's why I put it in here. So at the given time, at t is equal to 0, or at the initially, so it has x a comma x y comma x t. Then after it's going to move, so it's going to have some displacement. So that's where this point A dash represents. So that's pretty basic. So next slide is utterly the most important slide, and since I'm an engineer, I don't know how to explain this as a physicist. They derived this equation a long time ago, and I really don't know how to derive this equation, but I'm gonna give you the basic summary of what is it. So hence the lattice Boltzmann equation as follows. So first part is easy to understand. If you look at the streaming part, so we know that the first part is after it moved the a prime. The second part is minus f the initial. So it's like a streaming. So it makes sense. The particle moving to the one of the particles. So that's streaming. That's easy to understand. So the second part is the collision. That's something really complex for me, but I'm going to give you but before I explain to it, but I'm going to give you what is simple, because there are two extra terms in there. So first is FEQ, so that means F equilibrium, and then other one is at the very beginning, tau minus 1 over tau. So tau is the relaxation time. So what it means, like how long is it going to take a particle to relax. F equilibrium is like every particle has an equilibrium position or equilibrium state. So what that equation, that's a special equation to the calculator, and what that equation does is it'll calculate how long will it take, or what's the state of equilibrium for a given each and every point. So, and that's what is this equation. So the first part is streaming, the second part is collision. So it's like back and forth happening, streaming and collision. So yeah, so let's focus something important in here. F equilibrium. So it's defined as the particle distribution for particular density and the velocity, and a particular velocity when the fluid is reached equilibrium state. As I said, it's gonna at the given time, a particular time, it's gonna have particular density and a particular velocity because it's changing constantly, and defines the fluids the time to, or fluids the equilibrium state. suitable equilibrium equation is chosen based on the direction of the motion. Yeah, that is also one of the tricky part about this equation. So let's get through this. I don't want to get deeply how to derive this equation, but I just want to give you what are the things in here. So there are the equation, and we need to choose one based on, this is completely based on what direction. So first one is the density and the velocity. So if you look at the bottom, I have like v squared is equal to vx squared plus vy squared. So we have the velocity in x direction and y direction is a vector because of time and how it has a direction of motion. So we put that in there, and there's a so the first equation we use only for the central atom. The second equation we only use if the particle is moving axially. So particle from 2, 3, 4, the other one is going to have that. And the third one is particle moving diagonally, so 6, 7, 8, 9. So those are the so those three equations used based on how the particle is moving. So again, so first one is only for the particle at the center, but has no motion, so that's 0. And the second one is that particle is moving axially. The third one is particle is if the particle moves diagonally. So yeah, equilibrium equation continues. E1, E2 was a velocity vector component corresponding to the direction of the motion. As noted above, three particles exist. So the first one is at center, and the moving axially. The third one is a particle moves diagonally. So we look at a little bit deeper in here. In the equilibrium equation, every E, as in velocity, is defined in terms of x and y positions, or in vectors. So one at the center is at 0, 0, and if you look at the 2, which is on the right side, now in the diagram it's on the right side, it's 1, 0. Again, it's a conventional x and y direction, and this slide is pretty easy. Even this, so if you look at 6, it's on the right top corner in the diagram, so it's 1, 1. X is equal to 1, y is equal to 1. That's what it says on the left side, so right side of the presentation. E6 is a 1, 1. So this is, I don't have to go through. So let's get back to the boundary. So we mentioned the boundary conditions are easy to implement. That's why engineers love this method. It not only gives it the results really quickly, but also it gives the they can apply their boundary easily and get the results so quickly. So bounce back boundaries, there are lots of boundary conditions. We're just gonna look at two that which we're gonna use. So the last point, it says in there, at each wall streaming particle will collide and the surface will return in the same direction. Yeah, so it's gonna hit and come back. So we look at one of the boundary conditions is like if the imagine on the floor, you're dropping a ball, it's gonna hit the ball and it's gonna come back in the same direction. So that's what's happening. In most of the programming languages, we usually say new is equal to old. We don't usually say old is equal to new, because then that doesn't usually work, because you get an error. So in here, if you look at it, the picture, the 5 is hitting the surface and it's coming back as 3. If you look at the first equation, f temp, don't worry about the f temp, but it's just one of them. The way I wrote the code, I put it as f temp, the temporary. So the new one, so 5 is hitting the wall and 3 is coming back, so the 3 is the last procedure. So we're saying the last procedure is equal to the initial procedure. Same goes to 6. 6 is hitting the coming out on the right side, but 8 is the one is hitting. Don't think of it as a momentum, because people usually say it's hitting at 9, then it should come back at 6. No, we see in the previous page we said it's gonna return back in the same path but in the opposite direction. So that's what's happening in here, the bottom condition. The next one is like left fall. So if you look at 4 is hitting the wall and 2 is coming back. So that's what it says in the code. Everything is pretty straightforward. And the right false also says the same. And right now we have a corner boundary, so if you have a perpendicular corner, so in that corner 8 is going to hit and the 6 is going to come back. So that's what it says in the right in the code as well. F10 6 1 1. So because 1 1 is like the very first corner, x is equal to 1, y is equal to 1, then it's going to return back at 8. But sorry, 8 is hitting in from the point sorry, I made a mistake. 8 from the point 8 8. 8 is at the corner, it's going to hit the wall. So from 2 2 is going to go to the center, then it's going to come back. So that's what it says there. Then this slide is important. So microcalculation. So microcalculation is used to calculate how much density in that node, so by adding up all the F forces. So if I add up how much force in there, it will give me a sum. The sum will tell me, a Riemann sum, it will tell me how much the mass, or not, it's not a mass, but it will looking at density, like how much density is going to be in that each and every node. And that's also going to correspond to, and also if you want to calculate the velocity of that node, what we do is like we sum up the forces, but at the same time the forces has to be not forces, function. This function has to be multiplied by the corresponding e. The e what I mentioned is like e1, e2, e3, e4, or like when e is equal to 1, then 0 0. So f is completely 0. So you have to multiply them and add them all up. Then after that you have to divide by the density at that node. So that's how we'll get the velocity at that node, or resultant velocity. So, a couple of assumptions. We're going to use compressible flow like a liquid. So liquid in water especially, we know the density is equal to 1. So that's what it says in here. If the medium is incompressible, the density of the whole mesh is considered to be 1. Since we are calculating for the density of each node, the theoretical density must converge into value of 1. So we know that we are calculating for density of the every node from the previous node, but equals slide, but also we have to know that overall it should be 1. So after we add up the density, it should be equal to what? Well, most of my equation solution, I got the maximum value to be 1.003, still is equal to 1. And the second part is the tau. Like remember a long time ago we talked about the during the streaming and collision equation. There's one thing is like 1 minus 1 divided by tau. So this is the tau. So this tau is defined by 6 kinematic viscosity minus 1 divided by 2. It's a single reaction which used to control the how the system is approaching the equilibrium state. We have a multiple relaxation time, which is kind of complex, but there's a lot of way to calculate how fast the system is going to reach relax equilibrium. And also a small thing like kinematic viscosity is measured by the lattice unit. So we know the Reynolds number of the system and how much speed is going to disturb, and we know how much length of the system, so it's easy to calculate the kinematic viscosity. You can look it up on Google. So this is the basic algorithm that we're going to use to calculate or do the LBM. So first thing, we're going to create a initial parameters such as density, velocity, tau, which we just seen previously, and the first one is a single distribution particle distribution function. The second one is the F equilibrium function. We're gonna give this basic models, and we're gonna disturb the model, and we're gonna start calculating, and we're gonna calculate for n number of iteration until everything converges to the same values. So first thing we're going to calculate particle in motion, streaming. So when it's hit, the particle is moving, then when it's moved, come to another one point, we're gonna calculate what's the density at that point once it come to the node. And once we calculate the density and the velocity of the node, then we're gonna get the F equilibrium, because to calculate the F equilibrium we need density and velocity. Once we calculate the density and velocity, we're gonna assume it's hit the particle, now it's gonna move back, or stream after it collide, it's gonna move to the another particle. So that's when we calculate the F temp. In the temp, we calculate with the updated F equilibrium and the previous F, the initial F, we get F, and we get a F temp. We get this temporary value and put it back into the second step and update the number 2. Then it's going to move to the next particle. Then it's going to approach that particle, and at that, when you approach the particle, at that particle we're going to calculate the density velocity. And once it approaches the particle, we're going to calculate what's the F equilibrium, and it's going to go on and on and on until everything converges. So we are repeating from steps 2 to step 5 to get the results, or the LBM. That's how we calculate LBM. So a couple of notes: the values obtained from the intermediate steps 2 to 5 keep iteration and used in the next iteration, because we're not erasing that salts, we're keeping the values. And for the conversion purposes, we're going to use 200,000 iteration. Well, we can do less than that, but I do that 200,000 to make sure I get the results at the steady state. So we're going to test a scenario. So we're going to use the lead-driven cavity simulation, to just like classical method to test the LBM, and it's a very simple experiment. So imagine I have a box. In the side of the box I fill with water all the way to the top, and at the beginning the system is right, no motion, and the rest no motion, no inertia whatsoever. When t is equal to 0, I'm gonna disturb the particle. I'm gonna apply a constant speed at the x direction only at the top water. So using the LBM, I'm gonna see how where the vertex is gonna show up in this water if I make a cross section of it. So vertex is like a curve, like a round motion. So if you look, so the picture on the right, figure 16, but that's what it says. So I have a water all the way filled up to the top of the bucket, and the top I have like a treadmill or something like a belt bar. It's rotating constantly and disturbing the system. And we're going to test it for the following parameters. One is like when Reynolds number is 100, we're going to test it, speed is at 0.01, and we're going to test 0.1 velocity for the second, or RE is equal to 400,000, 2,000, 5,000, and 7,000 values. So also we know the initial density of the node is 1 everywhere, but each and every iteration we're gonna add, when we add up all the forces, we should get to 1 by convergence. And we're gonna use it grids of 257 by 257, and also we mentioned this at the boundaries, the speed is equal to 0. Alright, the next slide. So I wrote this code using Fortran, and I tested a Unix Linux-based system, and the results using after I run the result program, the results what I got, I used to tech plot to draw them, and I compare with this. These 3 results or equals research, I compare with, and these are really important. So the first one is, in the first time they used, let's just say, a grid size method, or using FHB method to simulate kinetic energy theorem, or the later derivative of kinetic energy theorem, which is the Navier-Stokes equation, used to compare the results. And they used the flowing grid size, and at the same time the solution they got the solution in 0.9 minutes for when R is equal to 100, which is pretty fast in 1982. And also the second, the second researchers happened the next year and came back and supported the previous results, and that was, everyone was happy, everyone was interested. Then the third one, that's one of the important things. So in 1985, they simulated the same results but using Lattice Boltzmann method. So the previous last two was Navier-Stokes equation, which include Boolean variables, but this one is used first time using single particle distribution function, and results were compared perfectly, and they also first implemented the boundary condition method, and this is something game changer in 1995. So if you're looking at the results in here, so if you look closely, so these two are I'm just giving you a picture of what is going to come up in the future, but it's just like a simple picture of like if you look at the top of each picture, you can see something red color. So what that means is like the water is moving really fast at the top, and as it comes down, it's slowing down. The middle, well, it wasn't exactly at the middle in the first picture, but if you look at the second picture, it's kind of the middle. It's kind of like a dark blue, so that means like water is really slow. It's like no motion or really slow motion. At the same time, at the walls, you can see really dark color because there's no motion at the walls. So if you keep going to the next picture, you can see really clearly the top is kind of red and the middle is blue. So if you look at the Reynolds number, as Reynolds number increases, the speed, it's kind of like increasing. Like you can see the picture on the right, when the Reynolds number is 2000, the system look like green, so like it has an intermediate speed in along the way. At the top, still like 0.1 meters per or speed is equal to 0.1, but which is high speed, but in the middle or the green section has the intermediate speed, and the corners still have zero velocities, or the boundaries or the walls. So this is the results that this is the summary of the result, and the ABC, on the left second column, it represents like previous results, and the D is my research result. Based on the results, as you can see, it's not exactly the same, but it's still within the range. So for instance, they got 6.196, I got 6.618, or they got 5.333, I got 5.338. So it's pretty much still within the range, off by 0.005. Well, I got the results, but just by zooming into manually, not mathematically, or like using a computer function, like just give me the exact point or anything like that. So that might be the reason why I'm off in the results, but you can see most of my results are pretty much dead on the previous researchers. It still supports that yes, I got the results as they did before using the simple Lattice Boltzmann method. So one of the observation in here, if you look at the central primary vortex, or we do call this primary vortex, which is the big one, it initially starts at the right top corner, then moves its way back to this exact center at the middle, 0.5. So that's one of the important note about this Lattice Boltzmann method results. And also there's like a third vortex are gonna propagate. So that's a primary vortex at the middle. Secondary vortex are coming at the lower two corners, and the third vortex are coming at the upper right corner at these given points. Then also there's like a fourth vortex at the very bottom, the small one is going to come at when Reynolds number is equal to 7,500. So this is the summary of the whole thing. So Lattice Boltzmann method is not as complex as Navier-Stokes equation, Lattice-Gauss automator, because Lattice-Gauss automator, they have the Boolean variables that are really complex to do, and boundary conditions are easy to implement. As I showed you before, the boundary conditions are simple equations, not simple, yeah, in the Fortran, and produces results in high accuracy. We remember seeing that hummingbird through yeah, like beautiful animation and accurate results. We can get the results by parallel programming, which is pretty much used every day current these days, and a lot of CF applications are using LBM, such as Pablo's, which is easy and free to use, and OpenLB, LBS, PowerFlow, XFlow, and many more applications are taking LBM and using it, but not in the grand scale, because SolidWorks and AutoCAD Fluid Flow, they're still sticking into Navier-Stokes equation. Well, the only reason is, as a mechanical engineer, when we do design let's say a box, or we already have like a huge matrix of that's gonna go into the just drawing that box in the AutoCAD or SolidWorks, and for them it's so simple because each block's already been filled up, and for only for that reason they still sticking into Navier-Stokes equations. But overall, like, and also this just came 15 years ago, the LBM method, but Navier-Stokes has been there for a really long time, so it's kind of like difficult for them to move from one to another, just like still America is still using British unit, the rest of the world is using metrics, but they can move from British to metric, but it's going to cost a lot in terms of money, time, and education, just like that. So it's gonna take a lot of research and development to go to Navier-Stokes equation, but if they did, that would be a great thing to happen to engineers overall. So that's pretty much it for my presentation. So what I did so far is I try to explain what is Lattice Boltzmann method and why is it being used, plus what are the good things. At the end, we saw an example of using Lattice Boltzmann method. We simulate the fluid flow in a little different cavity flow, but in future, if you're really interested in, we can do a lot of complex flows using the Lattice Boltzmann method, and all you have to do is, I have the basic thing, all I have to do is put like a boundary. That's it. Nothing changes. Thank you for your time.